right. Good afternoon. So we heard a lot in the morning about some of Mike Hochman's earlier results, and today we'll hear his own talk about the Borel generator.
Okay, thank you. So first I need to thank the other organizers than myself for asking me to speak. I don't object. One of the things that you can do when you're an organizer of a conference and a speaker is you can watch the abstracts come in one by one and try to choose your talk so it fits perfectly with the program. And so I was initially going to talk about one thing, and then there were so many talks in the morning session about that subject, I decided not to speak about it. But I can't resist dancing at both weddings, or having my cake and eating it too. So I do want to just to contribute to the morning session one result, and I won't really talk about it, and then I'll move on to Borel generators. So this really fits in with the last talk in the morning, and also the earlier ones, and this is an ongoing work with Boris Romiak. So actually it's not written yet, and so there's a chance that it's wrong, but I believe it enough to tell you about it. So the theorem is the following. Suppose you take a measure on SL2R, an atomic measure, so some convex combination of delta masses on matrices. So this is on, let's say GL2R. And you assume that, so gamma is the group generated by the AI, and you assume it's not, as we heard in the morning, it's non-compact and acts totally irreducibly. And you assume, then this tells you that there exists a unique stationary measure, mu stationary, on the one-dimensional projective space. And so now assume also, so as we heard, people are interested in when this is absolutely continuous, and you could also ask when is the dimension full, whatever full means here. So assume that the AI have algebraic entries and let's write chi for the Lyapunov exponent. And the conclusion then is that the dimension of the Furstenberg measure is the minimum of 1 and the entropy of mu as a discrete measure over 2 chi. Well, you can always normalize it, right? It doesn't.
No, but the Lyapunov exponent somehow. I mean, if you're working on the boundary, it doesn't. You sort of multiply each matrix by 2. It doesn't make a difference, right?
Yeah, it doesn't matter. You're right. It doesn't make any difference. Yeah. Okay. So SL2R. Sorry?
For this statement, don't we need to assume that the semi-group is...
Oh, yes, of course, sorry. And yes, you're right. So assume that AI generate a free semigroup. Yeah, so of course you take one matrix, it's not going to help you. And so
when you say the Lyapunov exponent, are you referring to the random product?
Yes, I'm talking just about the limit of 1 over n log the norm of x1 up to xn. Well, xn up to x1, I guess, doesn't matter. Where these are IID copies distributed according to mu. Yes, so it's just the Diophantine condition you need. So it's the same type of result that we saw this morning in Peter's talk and implicitly in Pablo's talk. And we don't get absolute continuity, perhaps, with we have to talk to Peter about it. Perhaps it can be improved, although it seems delicate. But
Not known it's absolutely complete.
no, well, there are examples where it is, but
In general, counterexample is no.
certainly it doesn't have to be. So the dimension could be less than 1. So whether there are examples when the dimension is 1 and it's not absolutely continuous, this I don't know. This I don't know. Okay. Well, it doesn't matter, right? Because you're so Ilona is right. So you're acting on projective space. So you somehow don't want to. Oh. So the proof here goes through. Well, it's very similar to what Peter talked about. It's additive combinatorics on the line. When you go to SL3 acting on the P2, then the action is no longer conformal. So, and then it becomes difficult to. Well, we don't know how to analyze the dimension of things. What may be true is this may go over to SL2C and the Riemann sphere, but I'm not sure. Okay, as I said, we can talk about this offline. So the topic of my talk is Borel generators. And so before I introduce the problem, which is a little bit abstract, I want to go back and explain, I think everybody knows, but talk a little bit about the history of entropy theory and ergodic theory. So entropy was not invented in ergodic theory, of course. It was invented with the purpose of analyzing somehow in applied mathematics, in analyzing the capacity of channels, how much you can compress a signal, and so on. And the way, and my motivation for this problem, I had two motivations. One comes somehow from the classification of hyperbolic type dynamics, which I won't talk about, and the other is a very concrete combinatorial problem. You have a sequence of symbols, which is, well, it's not going to come from a stationary source in the usual probability sense, but it will, you have some ensemble of sequences and you want to compress them in a stationary way as well as you can. And the question is, how well can you compress? So you say you have a sequence of symbols drawn from 0, 1, and 2, 3 symbols, and you want to ask when can you compress them to 2 symbols in a stationary way. And so in ergodic theory, this idea was introduced by Kolmogorov to answer a problem of Halmos. Halmos had asked, are the 2-shift and 3-shift isomorphic? Kolmogorov realized that Shannon entropy tells you that they aren't, and he was slightly wrong, and Sinai corrected the definitions, and so that's how Kolmogorov-Sinai entropy came to be. And so when you look at the proof that the 3-shift and the 2-shift are not isomorphic, you could do it using topological entropy or measure theoretic entropy. With measure theoretic entropy, you introduce an invariant measure, the uniform product measure, and then you show that these two are not isomorphic. Even after throwing away null sets, they're still not isomorphic. Okay. So the problem I want to talk about is the same problem. You have a dynamical system and you want to represent it symbolically, but without invariant measures. So the setting is going to be that X is a standard Borel space, which just means that it's the unit interval with Borel subsets, with Borel sets. So there's a sigma algebra, which I'm suppressing in the notation. And you have an automorphism from X to X, which is measurable. And it's an automorphism. So it's it's injective and surjective, and for Borel, in this setting, for standard Borel spaces, that means that the inverse is also injective, surjective. And so this pair xt is a Borel system. And let's define a k coding of xt is a map pi from x to 1 to k to the z, which is measurable and equivariant. And let me also, let's also say injective. So I don't want to map just everything to a fixed point. I actually want to separate points. And so this, of course, is equivalent, the existence of such an object is equivalent to the existence of a k-set generator on X in the usual sense. If you just take if you have such a pi and you take the partition of X according to the symbol at 0 that a point is sent to, you get k subsets that partition X, and the sigma algebra generated by all the shifts and joins of this partition gives you the full sigma algebra because pi is injective. So asking for a k coding is the same as asking for a k-set generator of this space. But I want to emphasize that there is no measure here. Okay? So usually in ergodic theory, when you want a generator, you want to partition the space so that up to null sets, you've generated the whole sigma algebra. But here there is no measure. Okay? I actually want to generate the whole sigma algebra. Okay, so of course if I happen to have an invariant probability measure on X, and if I find a k coding that is a k-set generator in this strong sense, then it will also be a generator in the usual ergodic theory sense. And so if I have an invariant measure on X that has entropy log 3, then I have no chance of finding a 2 coding. Right? That's basic entropy theory. And so the question is, what happens if you don't have any invariant measures? And so this problem was asked by Benji in the 80s, or maybe a little bit earlier. And it simply asks if there are no invariant probability measures, does there exist a finite coding, maybe even a 2-set coding? So you've removed the obstruction that comes from Kolmogorov-Sinai entropy, and the question is, what happens? Well, if there are no invariant probability measures, there are no periodic points. Right? It's free by definition because you could put a finite mass on the orbit. And also, sometimes you require that it's only you're allowed to exclude wandering sets. It actually doesn't matter. So.
Please speak louder.
Under these assumptions, usually people say, okay, we can assume that X is a compact metric space and
right. So, okay, if it were a compact metric space and this were continuous, you would certainly have invariant probability measures. At the very least, you would have to change this. I'm going to give some concrete examples in a moment. Okay? You can always put a topology on X that is complete, separable metric, and T is metrizable, but you cannot always get compactness. Because if you could always get compactness and continuity, then you would always have invariant probability measures, and you'll see in a moment that you don't always have. So, okay, so before I give examples, let me tell you one thing that Benji proved. So there always exists, under these assumptions, an omega coding. By that I mean an injective map from X into, say, the integers to the Z, injective and measurable, and equivariant. Did I say equivariant before? I did. Okay, so you can always do it with countably many symbols. Okay, now let me show you some examples. So as I said, the reason I got to this problem was because of some work of Bouzy on classifying hyperbolic type systems, and it was easy to deal with somehow generic points and for invariant probability measures and understand what happens with them, and then you're left with all this other stuff and you don't know what to do with it. And some of the it's just very annoying and weird that you can't figure out what to do with it. So that's what drew me to this problem. So let me so because of Benji's result, this means that we can assume from now on that X is contained in some shift space. Well, A is infinite typically, but we can just assume that we're dealing with sequence spaces. Now, okay, so some notation. So let's say that So if I have a point in, if I have a sequence, then we're going to say it's regular if for every word of length n on the alphabet, the frequencies of appearances of that word exist. So there exists the limit as n goes to infinity of 1 over n sum n from 1 to n. Well, let me just say the number of I between 1 and n such that xi up to xi plus little n is equal to w, well, minus 1 equal to w1 up to wn. Okay, just the usual frequency counting function. Let me denote this by mu x of w. So it's regular if all of these frequencies exist. And then if this function mu x, which is defined on the cylinders of this space, if it extends to a countably additive measure, then we say mu, let's say mu, we say that x is generic for mu. This is not generic in the usual sense. There are no, somehow, it's not a compact space, and the space of continuous functions, anyway, this is what it means. Okay, it just means the frequencies exist for cylinders. Okay, so now let me give you some examples of what can happen.
Wait, Mike, another silly question. So,
Yeah.
Remind us about the extension, the Theodore extension. Isn't it? Why does it automatically extend?
Well, okay, so it could. I will show you in a minute. Okay, I guess. Well, what could happen, for example, is that when you sum over cylinders of length 1, it might not add to 1. Think of the sequence that has one occurrence of each symbol. Nothing appears with positive frequency. Nothing works the way you expect it to work. Let me start with some simpler examples, though. So the first thing you might look at is you can look at the set of points in A to the Z.
There should be a probability measure in this extendability assumption?
Yeah, okay. So yeah, of course it's non-negative, and it's certainly if you take, I guess I allow the empty word, and then this empty cylinder corresponding to the empty word is everything, and it certainly has mass 1. So, yeah. If it extends, no, it won't be a. Yeah. Okay, I see what you're saying. Countably additive probability. Thank you. Right. So when I say generic, I assume the limit is not defective.
The ones that for any one.
No, so regular means that for every block the frequencies exist. All blocks. All lengths, all n and all lengths, yeah. Okay? More questions? Okay, so first think about this example. So take all the sequences so that some word that appears in X has frequency 0. So for example, take, I don't know. It is what it is. So this is a Borel set. It's shift invariant. So it's a Borel subset of the shift space. It clearly supports no invariant probability measures, because the ergodic theorem tells you that if it did support such a measure, then this thing would contain generic points for the measure, and it doesn't, because it has something that appears with frequency 0. Okay, so you can ask yourself, can you code this with 2 symbols? You have an infinite alphabet. So the fact that one symbol, let's say the symbol 0 appears here with very low density, the rest of the symbols appear here with very high density. You're completely free to put anything you want. So can you code it? Okay, that's one example. Here's another example. Take all the points which are not regular. Okay. Again, this is an enormous set. In fact, this is a dense G delta subset. So topologically, it's most of the space. Again, it cannot support an invariant measure, invariant probability measure, because if it did, it would support an ergodic one, and then there would be generic points that are regular. Okay? So there are no invariant probability measures on this thing, but you have enormous freedom. Even with three symbols, take the non-generic, non-regular points on three symbols, can you code them with two symbols, measurably and equivariantly? Okay, next thing you might consider, as Barak asked, you can look at points that are regular but not generic for a probability measure. What this means is that there's some partition of the space into cylinders so that the probabilities exist, but they don't sum to 1. So you have trivial examples of this. For example, at the ith coordinate put I, and then, well, this is a wandering, that sort of gives you a wandering example, but it's not so clear what to do with this. Can you define some kind of notion of entropy? It's again a very big set in many ways. And the last example to think about is you take points in A to the Z that are regular and generic for non-ergodic measures. I didn't say, but of course if you're generic for something, then the thing, whatever it is shift invariant. Okay? Now, okay, this is the last example is sort of the weirdest one, because on the one hand it doesn't support any invariant probability measures, because invariant probability measures, even when they're not ergodic, they're supported on generic points for the ergodic components. So there are no invariant probability measures here. And if you ask yourself, can you code this with two symbols? Well, the entropy of the limiting measure, even though it's not ergodic, does not have to be bounded. It does not have to be finite. You could be generic for an infinite entropy thing, or you could be generic for someone whose ergodic components have finite entropy but are unbounded. And you can imagine all kinds of situations. And so again, the question is there some kind of entropy that measures how many symbols you need to code this type of space, or this, or this?
About the last one, is it clear this is a Borel set? A set of non-ergodic measures?
Yeah, I think you can. And yeah, I think. I'm sure it is. I haven't. If not, then you can take a specific non-ergodic measure and think about that set. If that.
Collection of all non-ergodic measures?
The ergodic measures form the Borel. Generic points, ergodic measures form the Borel. And generic points form the Borel. Generic. We're not. Just a set.
Okay, so. Okay, so let me yeah, measurability is not the problem here. Okay, so yeah, so
Can you clarify the last example? Just give a point, specific point that's ergodic. Is that
well,
generic for a non-ergodic measure?
well, it's sort of okay, not an interesting one, but you take 1, 0, 2 1s, 2 0s, 3 1s, 3 0s, 4 1s, 4 0s, and concatenate like that. It's going to be generic for the point mass on the fixed point 0 and the fixed point 1. But yeah, but it's a non-ergodic measure. And it's an exercise to show that you can, mix and match anything you want and get weird things. So there are a lot. This is a very big set. I mean, basically any invariant measure has a generic point in this setting. It's not an issue. So okay, so let me make some remarks. about the general case and also here. So there are no invariant probability measures. Well, sort of by assumption, or in these examples, in each case by the ergodic theorem, but there may be, and there usually are, infinite invariant measures, or non-singular measures, and or, well, usually there's always both. If there's one, there's both. Non-singular. And we saw that ergodic measures, invariant probability measures of high entropy do form an obstruction to efficient coding, right? So you can ask, what about these guys? And so the answer is that by a theorem of Krengel, any such measure admits a two-set generator or a two-coding on a set of full measure. So in the infinite measure and non-singular worlds, there is no information theoretic interpretation of entropy of the kind you're used to. So these guys pose no obstruction in principle to coding. More than that, so you're able to get a coding almost everywhere for every non-singular measure. Well, when I say non-singular, I mean not equivalent to a finite measure. There's the theorem by Shelach and Weiss, which I'm not going to state precisely, but it says that the infinite and non-singular, by which I mean type 3, for those who know what that means, measures, well, cover essentially all of X. So, right, if you think about ergodic theory, topological dynamics, you can have a topological system and it might have an invariant measure which is not fully supported. And so there could be stuff left over. In this setting, the stuff that's left over after you remove a set of full measure for each infinite or non-singular measure is basically a wandering set. So there's nothing left over. Okay, there may not be invariant measures everywhere, invariant probability measures that cover the whole thing, but you can basically cover everything with these weird guys.
What does it cover?
What does cover mean? Well, okay, it means that it means that the only sets that are not charged for some non-singular measure can be covered by countably many wandering sets. No. It can be general. So, okay, if you take this and Krengel's theorem together, I haven't stated this precisely, but take it as it is, you can code almost all of every non-singular measure with two symbols, and those measures cover everything. So maybe you can glue them together and get a two-coding of everything somehow. But there's another fact, which I think is Benji's, or maybe Shelach and Benji's, which says that there is no quote-unquote ergodic decomposition in this setting. What that means is, in ergodic theory, if you have a Borel map, that's an old known thing? Okay. Okay, so folklore. I know it from a paper of yours, but so you cannot partition the space into disjoint Borel sets so that each one supports a single non-singular measure. It just cannot be done. Okay, if you support one non-singular measure, then you already support uncountably many non-singular measures of every Krieger type, and it's a huge mess. So there is no hope, at least technically, of combining this and that to get a two-coding of these types of systems. Okay, and one other, but in any case, Krengel's theorem shows you that there's no obstruction from the non-singular measures. And one more fact I want to point out, it turns out in the end not to be relevant, but it certainly looks relevant on the face of it, maybe invariant countably additive, finitely additive measures pose an obstruction. Maybe you can define some kind of entropy for these guys, and these guys exist. They're also plentiful. You always have them. And maybe some kind of entropy defined using them would prevent. I mean, all these sets look like they have very high entropy. Maybe you can see it through these guys. Okay, so all this build up. If you read my abstract, then you know that all this is just smoke in your eyes. So there are two results. So the first one is by Sarunian. Was published in 2015. It's from her thesis. So it's substantially older. It's maybe 2010. I'm not sure exactly. And what she showed is that if X is locally compact, T continuous, and no invariant probability measures, then there exists a finite coding. And I think she gets some concrete number for that finite coding. It's not 2, but it's something.
I think it's 32.
Yeah, okay. It's some finite number. And actually, it's not so hard to go from 32 to 2. Once I think.
So this is example.
No, this is an answer for a class of maps. So in general, as I said, you can always introduce a topology that makes you complete metric separable in T continuous. And she needs more than complete metric separable. She needs locally compact. So it's restrictive. Sigma compact? Okay, Polish is given. It's a Borel space. But okay, yeah, okay, maybe you're right. Okay, sigma compact. Yeah. Yeah, okay.
Size of the coding does not depend on X.
No. And in fact, she gets this result for any countable group acting on such a space. And the number of symbols that you need depends somehow on the group.
No, always 32.
Always 32? Okay. Well.
That's also dependent.
Sorry?
That's also dependent.
It also depends, yes. Okay. So so the theorem that I am telling you about today, and it's also 15, but it hasn't. So there's a gap between these. Yeah, it's not the same. They're not simultaneous. Is that it's always true. There always exists a 2 coding. So you can always code. So in those 4 examples I gave you, for example, you can always code with 2 symbols. In Z, I'm talking only about Z. Yeah, and it's a question whether you can do it for any group. And I believe that my proof can be adapted to countable amenable groups. Shouldn't be. I mean, it will be hard and painful to do it, but I think it can be done. But the proof that I will sort of sketch for you very quickly now very much depends on entropy and averages and all kinds of things that you cannot, on the face of it, do for general groups.
So we don't have the same condition for sigma compact.
No. So for any,
All this means
for Benji's problem. No, for Benji's problem. So if xt is a Borel system without invariant probability measures, then there exists a 2 coding. Okay, so how does the proof go? I don't have much time to tell you about it. I want to tell you sort of a reduction that reduces it to 3 of those cases that I had on the board before. Okay, and it's based on a theorem of Dotkarny, which says the following. So suppose that xt, let me try that again. So a Borel system xt has no invariant probability measures if and only if, so it's a characterization, if and only if there exist measurable sets D and a sequence of sets A1, A2, and so on, such that, so first of all, let me call it alpha. The collection AI is a partition of X. The set D is sweeping out. What it means is that every orbit meets it. So X is the union of Tn D n from minus infinity to infinity. So every orbit meets D. So in some sense, D is not trivial. And there exist integers n1, n2, n3, and so on, such that the complement of D is the union of Tni ai, the disjoint union of Tni ai, I from 1 to infinity. So let me draw a picture of this. So what this says is that you can do the following thing. You can, here's X, and you can partition X into sets A1, A2, A3, and so on. And then you can find another set D, which is large. So it meets every orbit, that means it's large. So for example, it means that every invariant measure gives it positive mass, I guess. Certainly every invariant probability measure if they exist. And then what you can do is you can map each of these AIs by some power of T into, so this is Tn1, A1, this is Tn2, A2, and so on. You can map each piece into the complement of D. Now, it's easy to see that that this is impossible if you have invariant probability measures. If you had an invariant probability measure, it would have to give D positive mass, because because every orbit meets D. So by the ergodic theorem, it has to have positive mass. Or by
X is countable.
sorry?
X is the union of countable.
Yeah. Okay, thank you. Yeah. And then, but on the other hand, the masses of the AIs have to sum to 1. But then you translate them to pieces that have the same mass, and they sum to less than 1 because they sum to less than 1. So this doesn't happen. And the amazing thing is that this is a characterization. If you do not have invariant probability measures, then you have this structure.
So it must be, hope must be mentioned.
Yeah, so Hope has a version of this when there's a measure involved. Yes. So this is the Borel analog of Hope's theorem. Yeah, so Hope has a characterization of when there exists, I think, an equivalent invariant probability measure. Okay, so now assume that there are no invariant. So assume that there are no invariant probability measures. So that means that you have such a family of sets. And now I'm going to partition X into 3 pieces. The first piece, I'm going to call it X no, is going to be all the sets X, all the points X that visit D with frequency 0. Okay? So this is the analog of the first example I gave you. So it might be an empty set, might not. Okay, next, let's define X irregular. Let's call it ir for irregular. This is all the points X that visit some AI without limiting frequencies. Okay. So this is sort of the analog of a non-generic point. You have, and it's really the union of countably many sets, each of which is the set of points which are somehow not generic with respect to the indicator function of AI. And then let's take, let me call it def for deficient or defective. This will be the complement. So x minus x null union x here. And I claim that points in this set somehow behave like the defective points that I had before. They exhibit somehow statistical behavior, but they don't look like they converge to a probability measure. And the reason is, so if you have a point here, then you can let's define mu xi to be the frequency of visits to AI, which exists because you're not in the irregular set. Then clearly the sum, so this is also the frequency of visits to TNI AI, obviously. So, but the sum, right, TNI AI are contained in x minus d. And so the sum of mu xi from 1 to n, this is less than the frequency of visits of x to x minus d, which is less than 1 minus mu x of d. This is positive. Well, less than or equal. Well, equal actually. This is positive because x is not in x null. And so if so,
What if this doesn't exist?
well, the frequency to d exists. Ah, no, you're right. So you're right. So in the irregular, I have to add also to d. So visits some AI or d maybe don't exist.
Like just because the frequency to AI exists, so these frequencies could not add up to 1.
I mean, the frequency to here is not 0. So I don't know. There's maybe a limb soup somewhere instead of a limb, but yeah. But if you want, you can add d to there, and that's okay. Okay, so this is not a partition of x. I mean, you could be here and here at the same time, but you have 3 chunks of x, and each of them is basically like one of those examples I gave you before, the first 3. And okay, I won't have time to really tell you about the proof, but let me say a word about how each part goes. So dealing with points that visit a set with frequency 0 is easy, or at least it's not hard. It's very similar to Krengel's theorem. So what it's not the way that Krengel does it, but if you have an infinite invariant measure, then you can find a set of positive measure where points visit it with frequency 0. And then when you look along an orbit, you have this 0 density set of times, and the complement is much bigger than the set of visits, and you can somehow use that to, well, it gives you a lot of space to code. I won't explain it, but this is basically like the infinite measure, invariant measure case, which was known. What do you do in the irregular case? So this case I like very much. I was hoping to tell you more about it, but what the proof requires is to get some quantitative information about how things fluctuate. Now there's a version of the ergodic theorem which is due to Bishop, which is effective, and it gives you an upcrossing inequality for the ergodic theorem. It says that if you have an invariant probability measure on some system and you have a function and the limits don't exist for some point, then the set of points, if you take two values, arbitrary numbers, a less than b, and you look at the set of points which, so that the averages of an orbit, of the function along an orbit, visit alternately above b, then below a, then above b, then below a, infinitely often, the fact that has measure 0 is just the ergodic theorem, because well, you know that almost every point the averages converge. But Bishop's theorem tells you that if you ask what's the measure of the points where the averages fluctuate above B and below A n times, that probability decays at a universal rate, which depends only on the norm of F. Okay? It's a very nice theorem. It's somehow the closest thing you can get to a rate of convergence in the ergodic theorem. And what goes into the proof of this? Well, there's a coding algorithm for points that show irregular behavior. And the key fact is that you can control the density along the orbit of the point where you see many fluctuations. So that's vague. You can look at the paper if you want to know more. The hardest case to deal with is these defective points. And for the defective points, what you end up doing is proving a Krieger generator theorem for empirical frequencies. So this is the case where you have empirical frequencies. You know the point visits these sets AI with some specific frequency, but they don't sum to 1. And you can, but they still might look like they have high empirical entropy in some sense. But you can somehow push this entropy down and give an entropy, a classical entropy argument that codes them with 2 symbols. Okay, I've hidden a lot of details here. So it's a very strange proof, for especially the third part, because you're trying to prove something that sort of contradicts what your intuition about entropy, but you end up using classical entropy theory to prove it. So I think it's kind of strange. Okay, so let me finish with an open problem. So I mentioned one open problem earlier when Russ asked about, or maybe I don't remember exactly, but the question of what happens for other groups is open. So that's one question. Actually, I have 2 more. So second question is, let me write down again the 4th example that I gave before. So you look at the x's in A to the z, which are regular, which are generic for non-ergodic measures. And so we now know that you can code this with 2 symbols, but I don't actually know how to do it. So the other cases essentially appear in the proof of the general claim, and in each of them there is a concrete algorithm, at least in some sense concrete, that codes for you. To code this case, what I know how to do is apply Nadkarni's theorem, which is very abstract, and then go through the whole routine of reducing to the 3 other cases. So it's not a terribly important question, but it's a little bit strange, such a concrete example that you can't code it directly by some clever trick. So that's one thing I'm curious about. The other thing, so to explain the other question, let me say why Benji's problem came up in the first place. Well, okay, he was interested in doing ergodic theory in this category, and this would be a natural isomorphism invariant. If you could, isomorphism between 2 Borel systems means you have a measurable bijection between them that intertwines the actions, and you would like to maybe classify or get some kind of classification of these systems. If there was some notion of entropy, you would have some classification, and the how efficiently you can code is closely connected to entropy. But as it turns out, this gives you nothing. You can't distinguish this type of systems without invariant probability measures. You cannot distinguish based on this. So I want to give you, let me give you two systems, very, very concrete systems, where I don't know whether they're isomorphic or not, and you'll see how sad the situation is. So consider the following 2 systems. One is, well, we saw it before. Let's just look at the irregular points that are not generic for anything. So this is a very wild set. It's in some sense most of this Bernoulli shift, right? And the second set, so you take a non-locally compact monothetic group G generated by some little g0. Okay, so that means that it's an abelian group with a complete metric on it, which is just the closure of all the powers of one element in it. And then you just take translation by G, by G0. Okay. Now, okay, this we already know doesn't have invariant probability measures on it. This doesn't have invariant probability measures on it because an invariant probability measure would be invariant under G0, therefore under all of its iterates, therefore under the closure of all of its iterates, and you would get a finite Haar measure on a non-locally compact group. Okay. I guess I just need non-compact really. And so again, there are no invariant probability measures on this. Are they isomorphic? This is the question. So Bernoulli shift, group rotation, we don't know if they're isomorphic. It's a little bit ridiculous. But they both can be two-coded, so the intuition of entropy is incorrect. Okay, I'll stop here.
Any additional questions?
Yes?
Tell me please, what is application of your theory which you cover by usual algorithm? Application of your entropy theory for pathological Borel case,
Well,
which are not. Please give me an example.
yeah, okay. So
It's well known that Borel dynamics sometimes is useful, but of course is not.
Well, okay, so
can be compared with measure theoretical and topological dynamics.
okay, let me tell you one application of this, concrete application of this, which there are no very dramatic applications that I know of. But okay, another problem. So I'll describe two subshifts for you. Okay, the first one is just the full two shift. Okay, the second one is the set of sequences on three symbols, so that yi is different from yi plus 1 for all I. Okay, they're both shifts of finite type of entropy log 2. Okay, and they're not isomorphic. This one has a fixed point, this one doesn't. Okay, now let's define x prime to be just x minus the periodic points, and y prime to be y minus the periodic points. So I've killed the obstruction of the fixed point and anything related to it. Now you can ask, are these systems isomorphic in the Borel sense? And the answer is yes. First you deal with the invariant probability measures, so you can identify the whole thing. And as I said, I got to this because Bouzy was interested in this type of question, not for shifts of finite type, but for a much broader class of dynamical systems. Can you identify the entire Borel structure? Okay, so a problem. So they are measurably isomorphic. Does there exist a continuous conjugacy from x prime to y prime? This I don't know. There's no invariant that can distinguish at this point. Okay.
We have time for one more question.
I just wanted to ask if you have some invariant measures on the system, but they have very small amplitudes.
Yeah, so you can yeah, so that's what determines. If all invariant probability measures have entropy less than log k, then you can code with k symbols. Yeah. What you expect.
Thanks, Mike, again. So we now have a break.